Hi guys, BuildZoid here, and today we're going to be taking a look-see at an RTX 2070 Super KO edition from EVGA. Now, the KO, as far as I can tell, stands for cost optimized, and they did so much cost optimizing that they couldn't even afford to spell it right, which is why it's KO and not CO. But yeah, the idea behind the KO edition cards is that they're supposed to be cheap. Now, unfortunately, the 2070 Super KO is not really the cheapest 2070 Super you can buy. Like, it's one of the cheaper models, but it's not the straight up cheapest at the time of this recording this video. Um, yeah, and we're not going to be. This is not going to be like a full on PCB breakdown. Partly because I can't get the specs for all of the components. Partly because I also don't care that much to do a full PCB breakdown of yet another 2070 Super, especially one as unspecial as a KO edition. But what this is going to be is a comparison between the KO edition and the reference card, because well, let's take a look at the cost optimization. That is the idea behind this video. And before we get into this, the pictures are from Tech Power Up's review of the 2070 Super KO and the 2070 Super Founders Edition. So huge thanks to them for the pictures. I'm going to leave links to their reviews of both of these cards down in the description below. So yeah, if you want things like temperatures, performance, noise, you know, the actual like real world performance metrics, you can go check those out. But that's not what this video is about. This video is about removing components and down costing components to just make a cheaper card. So, you know, let's get into it. So the first and most obvious adjustment is the removal of this phase right here. So the reference card is an 8+2 phase, where you've got 8-phase V-core and 2-phase memory power. EVGA is running a 7+2 phase, where you've got 7-phase V-core, 2-phase memory power. And well, they achieve that by just throwing this phase right out, right? Like you remove an inductor, you remove a power stage, and apparently a pair of capacitors, and obviously that's going to be cheaper than including those. So that's the first cost optimization step right here. Then not so noticeable is the fact that these are different power stages. Oh well, pretty noticeable, but I guess it's like okay. So anyway, different power stages. The reference card uses a bunch of 70 amp smart power stages from Fairchild Semiconductor. Now, these are not the most expensive 70 amp smart power stages you can get. They're also not really like the most efficient ones you can get. But they're still 70 amp smart power stages, so they're not exactly cheap, at least as far as power stages go. Whereas these, well, these are in a 5x5 millimeter package, and I can't identify them, which is kind of like I can identify most MOSFETs most power stages these days from like bigger brands. So it's just like, yeah, I don't know who's making these. I'd be very surprised, but like this package size, I'm not aware of a power stage with more than a 60 amp rating in this package size. I'd be very surprised if these are rated for even 60 amps. I'd expect these to be like 50 amp power stages, but ultimately, even if they were 60s, that's still weaker than what you get on the reference card, and the reasoning is obvious. It's like, well, they're cheaper, right? So we've got some cheaper power stages, which, yeah, that's not surprising, right? Like, you remove phases, then you down cost then you just cost optimize the phases that you do still have, right? Like, first you remove the unnecessary one, and then you shave as much as you can off of the ones that are still left. Then we've got capacitor adjustments. That's a very big visual difference, so that's pretty obvious. So the reference card uses a bunch of these lovely SMD aluminum polymers that I would guess are from Panasonic. I'm not 100% certain about that because, well, there's kind of a lot of black SMD aluminum. Like, I'm assuming that there's somebody else who does also black SMD aluminum polymers. It's just that this is a package style that Panasonic uses. And then like APAC does SMD aluminum polymers, but those look like this, you know. So those are very like these are APACs. These are probably Panasonics. Anyway, SMD aluminum polymers are great. They give you a low ESR and a really low ESL compared to through-hole SMD aluminum. I mean through-hole aluminum polymers. Not, I don't know why I was putting SMD in there. Though, to be fair, you can also get the can. Well, I should really just call them cans, because you can get the can polymers with SMD mounts as well. But yeah, this style of aluminum polymer has much lower ESL than this style of aluminum polymer. There's one downside to these down here. They're more expensive, and you can't get them in endurance ratings higher than like 2,000 hours at 105 degrees. On the other hand, with these, you can get them in 5,000 hours rating at 5,000 hours, 105 degrees. You can get them very, very cheaply, and their ESL sucks relative to the SMD capacitors, at least. So, yeah, essentially what EVGA is doing here is they're giving up some transient response performance to lower the cost of the capacitors just kind of everywhere. At the same time, they are probably, like, these capacitors will probably have a better long-term endurance, but, like, you're starting with a weaker performing capacitor in the first place, and then like, if the VRM doesn't run particularly hot, even a 2,000 hour capacitor can last for ages if you just don't run it that hot. So, yeah, that's the thing, is like the high endurance rating is not necessarily that useful unless you have cooling problems. So, yeah, anyway, moving on from the capacitors, we have the inductors of the memory VRM. So, you can't really axe a phase in the memory VRM, unfortunately. At least I don't think so. As so far, I've not, like basically for GDDR6 cards, it seems to be a bare minimum requirement to have at least 2 phases, probably from a like voltage regulation requirement, not so much from a, like, I don't think it's from a power handling requirement, because you can technically build some really ridiculous single phase VRM designs. Just look at like the memory power delivery of an R9 290X. Right? That's a single phase memory VRM powering 512 bits worth of GDDR5. Like, if you can do that, you don't need a 2-phase for 256 bits of GDDR6. And ultimately, like, as far as I can tell, but I assume from a voltage regulation perspective, you just need a 2-phase for GDDR6. Anyway, so they can't chop a phase off, so instead the phases that, instead, make the phases cheaper. And, well, for the inductors, there's not really that many things you can do to inductors to try get them cheaper, because inductors are kind of simple components. You've got a core and you've got some wire, and the wire either runs around the core or through the core or does some fancy combination of the two things, but ultimately you have a core and some wire. The thickness of the wire basically sets how much current the wire can handle. So obviously a thicker wire means more copper, means more expensive, especially if you want a high inductance, because then you potentially need to have, like, some turns in the wire to get the higher inductance, and then it's like, okay, now the wire is also longer, not just thicker, and so that's just more copper, more expensive than less copper. Similarly, the core material, like with the core, if you want a certain amount of inductance, you need more core. You need more core material. Core material is expensive, so the best way to down cost an inductor is to just make it smaller. Now, if you're making an inductor smaller, you have 2 options for things you can adjust. You can have less inductance, or you can have less current handling capability. Current handling capability is not something you can just freely throw out the window, because if your GDDR6 memory chips want 20 amps, then you need to provide 20 amps. You don't really have a choice in that. So you can't exactly go and use like a 5 amp inductor on a, 2 5 amp inductors on a 20 amp VRM. Like, that's just not going to work very well. More like you're probably going to burn the inductors eventually. But you can just drop the inductance down. So that's what we see EVGA has done here, right? These are 150 nanohenries, and we know that because it says R15 on them, whereas the reference card uses R47s. So these are 470 nanohenry inductors, which is really high, actually. Like, surprisingly high. Now, what's the downside to the lower inductance? Well, the lower inductance means worse efficiency. It can also mean a slight improvement in terms of transient response, but that also depends on how the controller behaves, and and you know, other VRM design considerations. But one thing that never changes: if you reduce the inductance of your inductors, the efficiency goes down. And the reason why your efficiency goes down is that the peak current flowing through your phases goes up as the inductance is reduced. So as the peak current goes up, your I squared R losses get worse. So yeah, lower inductance inductors make the memory VRM somewhat less efficient. And then we've also, like, you know, 70 amp smart power stages, very expensive. You know what's cheaper than 70 amp smart power stages? Well, in the VCore VRM, we've got cheaper power stages. But you know what's even cheaper than cheap power stages? Dual NFETs, right? And that's exactly what we got here. So these are just basically two MOSFETs in one package. This is even cheaper than a power stage, and the only issue with this is now you need to provide your own drivers. But luckily, two-phase voltage controllers with integrated driver circuitry are very common and also rather cheap. So that's exactly what we got over here. Unfortunately, I don't have the part number for that chip, but yeah, that's like... it's probably some generic UPI part that we've seen on a bunch of other 10 or 20 series cards before, so it doesn't really matter that much. On the other hand, the Nvidia card does goes with a UP9512, which is an 8-phase controller used for VCore VRMs most of the time, but you know, Nvidia just it's Nvidia. They don't really care about massively cost. Well, the funny thing is, old Nvidia cards would actually be very cost optimized on their reference PCBs, but it seems like with the 10 series and especially the 20 series, Nvidia has just kind of ditched the old policy of making some of the cheapest PCBs possible. Yeah, we've got a really kind of massively overkill voltage controller for our two-phase memory VRM here, whereas EVGA is going with, you know, again, a more cost-optimized option. So that's sort of the major changes to the VRM, right? To the actual power delivery is we've got less phases in the VCore, cheaper power stages in VCore, cheaper capacitors everywhere, smaller inductors for memory power, cheaper MOSFETs for memory power, cheaper controller for memory power. So that's the main changes right there. Then over here on the output side of on the display output side of the card, you'll notice that there's no Type-C port, which also means we can get rid of the USB Type-C voltage regulator. Which is like this circuitry down here on the reference card. Yeah, that's gone. We don't need that anymore because there's no USB Type-C output on this card. So it's another cost-saving measure right there. And now let's take a look at the input circuitry, because on the reference card you get all of this well, actually, I think it's really pointless, but you get all of this current balancing circuitry, and there is a lot of it. And then you need, so that's your current balancing MOSFETs. Now, MOSFETs are dumb, so you need some kind of controller for every single one of your MOSFETs, and in this case, that's a bunch of these chips over here, and we've got 4 of them in total, so we've got all of these current balancing controllers, and then we've got our MOSFETs for those. You know, so that's you know, that's part, so that's cost. And then because we have all of these different like 12-volt channels now, because Nvidia just, like, I don't know why they do this. It doesn't make it, like, if you look at AMD cards, they'll literally just take the 8-pin and the 6-pin, run it through an inductor for some ripple suppression, and then go straight to the VRM. Like, no current balance, no current monitoring. If our card pulls too much, if our card goes out of spec, well, let's just hope it doesn't do that. That's essentially how the RX 480 manages to violate the PCIe power consumption spec. Is like AMD GPUs are literally incapable of measuring how much power they're pulling because AMD is just not bothered with including that kind of circuitry on their cards. Nvidia, on the other hand, is, and then they've implemented power limits that are so strict that they also need to include all of this extra power balancing circuitry. So, yeah, and Nvidia is literally making more work for themselves, but I mean, they're also using an 8-phase controller for a 2-phase VRM, so obviously cost is not much of a concern here. Though this actually could potentially be a cost optimization thing, just because, like, instead of sourcing 2 different chips, you could source 1 chip and use it twice, but, you know, that's far too reasonable. They're just being expensive for no reason. That's totally the reason why that's there. Anyway... so you have all of this lovely current balancing circuitry, and then you also need to be able to monitor where all of this current is going and how much of this current is going where. And that's why we also have all of these shunt resistors. So you've got these 3 white ones, And then you've got the main input filtering. And then you've got these three main input shunts. So one for an 8-pin, one for the 8-pin, one for the 6-pin, one for the PCIe slot, right? And then you've got the white shunts for the current balancing circuitry. And now you have 6 shunt resistors, so you need 2 shunt monitoring chips instead of just one, because this chip right over here, that's an NCP 45491. The NCP 45491 can only monitor 4 shunt resistors. So if you've got 6 on your cardware, you're going to need another NCP 45491. So that's exactly what Nvidia has done, and that's why we have 2 of them, which obviously makes the card more expensive again, because it's just like, it's a whole extra chip because you decided to monitor that. Like, why is there current balancing? I can understand monitoring the input power consumption, like how much power is going into the card, monitoring that. Okay, I could kind of understand that. Like, I get, like, AMD doesn't bother with that, but, you know, that actually is honestly kind of weird. But then we've got the Nvidia end of that, where it's just like, first we monitor the power, and then we have to balance the power, and then we need to monitor the balancing of the power, because otherwise you can't actually do any balancing, right? So yeah, this is a lovely way to make 12-volt power distribution way more complicated than it needs to be. Praise be to Nvidia. Anyway, so EVGA came to the same conclusion that I've come to about all of this current balancing stuff, and that is basically that it's unnecessary and costs money, waste of board space, waste of resources, shouldn't be present on the card. And that's exactly what they've done, because we can see the remnants of a lot of current balancing circuitry right here and here, or more like the footprints for it. And then EVGA just kind of decided, yeah, but the card won't be very cheap. So you know what? We don't need that. Get rid of it. And as a result, they also get rid of all of the current balancing controllers, but they didn't get rid of all of the current balancing MOSFETs. And I think these are just controlled with like discrete circuitry. Like, I'm not entirely like I'd assume this is being used to like control these, or maybe it's some of these transistors over here, because essentially, like, I don't think you can actually ship I don't think Nvidia would approve a PCB design without at least some current balancing, just because of how ridiculously restrictive their power limits are. But, yeah, you know, this is a lot less current balancing than what you get on the Nvidia card. And you also got a lot less shunt resistors. We've got this one over here, we got this one, and this one. Therefore, EVGA can get away with just one current monitoring chip, and that chip is not a is not an NCP 45491. It is a US 5650, I think. I might be wrong about that. It might be, no, it's 5650. That's the part number. But yeah, that's a 4-channel current monitoring chip, not balancing. It doesn't have any well, it has an output, but it's not able to directly drive MOSFETs or something like that. So yeah, that's just there to monitor the current coming into the card from the 8-pin, the 6-pin, going towards, I think, one phase of the memory VRM, and coming in from the PCIe slot, right? So I assume most of this current balancing actually is just like changing where the memory VRM pulls some of its power instead of like current balancing the vCore. I assume this is just fixed in terms of how it's distributed between the 6-pin and 8-pin. So far, EVGA has been doing a great job of just slashing and downcosting anything that isn't necessary for the operation of the card. But they did actually make some additions. They've added fuses on the inputs. Now, I don't really consider fuses a super useful feature for like end users. It's a great feature if you're basically the fuses are really nice if you're repairing a card, but they're completely and utterly useless if you don't know how to repair a card. So basically, they're good for like RMA departments and people who buy dead cards off of eBay, but they're completely useless to most end users because those fuses are there to minimize the amount of damage that a failed component can create. They're not there to prevent a failed component because they can't actually do that. They're not fast enough. So basically, if a MOSFET dies and you don't have a fuse and you have a power supply with a really slow short circuit protection, that MOSFET can potentially put a pretty massive crater straight through several layers of the PCB, which then means, you know, if you're like, you can't actually repair the card anymore because it's like, well, now we need a new PCB. Okay, like that would be like restoring the card to factory new condition would be like, we need a new PCB. If you have fuses and you're lucky enough that they blow fast enough, instead of the MOSFET putting a crater through the entire PCB, you can get away with the MOSFET maybe just breaking its own casing, right? Where you'll just have a bubble in the package, or you know, you won't have like damage going through several layers of the PCB. So you can just desolder the dead component and replace it with a new one, and the card will start running again. That's if the fuses work, you know, as you would hope they would work. A lot of the time they blow after major damage has already occurred, so they don't actually, like, they're not 100%, you know, reliable in preventing further damage, but they certainly do, you know, they can help. And I guess EVGA is adding them here because on a card this cost optimized, they're probably, you know, expecting maybe an ever so slightly higher failure rate. I don't think it would be like significantly higher. It might also be to stop people who are going to like blow out the power limit. Like if you wanted to shunt mod this card, those fuses might be there to not let the VRM die before the before the fuses blow. Basically, if you remove the power limit, like, you know, this VRM might not be adequate any longer, so those fuses are supposed to blow if you do something like that. Anyway, yeah, so we do have some fuses. Nvidia, on the other hand, doesn't really care about repairability, so no fuses for you. Yeah. Though, funnily enough, I have heard of like some Nvidia cards where if the VRM dies, the actual shunt resistors blow up instead of the VRM. A lot of the time, though, the VRM blows up, and then the shunt resistor blows up. So then you'll have 2 points of failure. And I have an actual theory because I've seen quite a few cards where the actual current balancing MOSFETs would blow up. And I don't think that's the MOSFETs themselves being undersized. I think what happens on those cards is first first your VRM dies, and then the current balancing circuitry also dies because of the, like, basically acts as a fuse for the VRM, because the VRM can probably soak up a bit more heat than the little MOSFET somewhere on the edge of the board with no real cooling. So, you know, if like a power stage fails short circuit and that power stage happens to be connected through the current balancing circuitry, well, there's a good chance that current balancing circuitry is going to take that, you know, short circuit a lot worse than the MOSFET is. Because, yeah, and that's just a theory I have. I don't actually repair enough cards to be able to confirm that actually happens, but like, it just doesn't make sense to me for the current balancing circuitry to blow up. Like, the MOSFETs shouldn't be under, like, those MOSFETs, they're not switching, you know, they're not doing any difficult work, or they shouldn't be switching too frequently. I guess if you're Nvidia and have this ridiculous current balancing scheme, then okay, probably they're doing a decent amount of switching. But, you know, if you got 2 of them, which a lot of older cards will have, like, they'll have like 2 or 4 of them, it's like, they really shouldn't be doing that much. So if they're blowing, it's probably because they're acting as a fuse for something else. Anyway, so, you know, the input fuses can help with minimizing a lot of damage. So with that, we've covered sort of everything I want to cover on the front of the board. You know, we've just got a lovely downcosting just everywhere. And now let's get to the back of the board. We've already kind of been here, right, for the control circuitry. That's gone. Oh, there's more missing current balancing stuff. So yeah, we don't need that. Just unnecessary. So, you know, on the back of the board, we're missing all of the extra controllers, extra current balancing, but I love the capacitor configuration for the memory chips in the core. Like, they've really gone all out. I mean, don't need these, don't need you, don't need you, nope, don't need any of that. These are extras, actually. These are not part of the reference design. I'm guessing what happened with these is EVGA was maybe considering replacing a lot of these larger multi-layer ceramics with just, like, large SMD polymers. But I guess they came to the conclusion that either that doesn't, like, that probably didn't work well enough that it would actually cost less, so they just didn't do that and left a bunch of blank pads on the card. Because, yeah, I'm not really sure why else they would have added the pads in the first place, right? Like, You could have, because the thing is, the actual capacitor configuration of the memory chips is basically identical to the reference card, except on the reference card, we don't have a bunch of empty capacitor pads, right? Like, you'll notice, like, that's, every single one is populated. Every single one of them, right? All populated. And then you look at the EVGA take on this, and it's just like, well, who needs these? These aren't important. Who cares about 50 megahertz worth of memory clock? And that actually is possible. I'm not sure that it's exactly 50, but I have messed around, like, with the very limited experience I have with GDDR6, which is literally 12080 Ti. Adding extra capacitance to the memory VRM did actually lead to better memory overclocking. So, you know, lopping off every single multi-layer ceramic that isn't necessary for the operation of the card in, at stock frequencies, probably isn't great for the overclocking prospects of the GDDR6 anymore, right? Considering that, because my experience was a reference 2080 Ti, and that's obviously not as downcosted as it could be. So, yeah, this right here is like, I would assume on average the 2070 Super KOs are not as good at memory overclocking as reference cards or other PCBs that actually have all of these capacitors populated, because at least in my experience, GDDR6 does seem to be, like, it definitely scales with voltage, and it might be rather, sensitive to having a whole lot of its filtering just get removed. But not enough so that the card won't run at stock anymore. It's just like, if the card could, if you had a card that literally couldn't overclock, and then you couldn't overclock at all on the memory, like if you went plus 10 megahertz, it crashed. That would be a card where removing a bunch of capacitors would probably stop the card from working. But yeah, no, this right here just, like, I guess this is nice reassurance for anybody who has a reference card and, like, knocks off a memory capacitor with a screwdriver or something, because EVGA right here with the KO, they're really proving that a lot of them are extremely redundant, right? Like, you really don't need all of these capacitors, because they are just chopping them off like there's no tomorrow. And don't need that, this, who cares? Don't need these, right? There are just missing capacitors everywhere. And we see more of the same right behind the core. It's not as obvious, but it's definitely there. Like, if we zoom in here, these are populated. These aren't. Nor is that. Nor is this or this. And that's ignoring the fact that they've completely changed just the general capacitor configuration behind the core. So if we look at the reference card, we have this lovely sea of multi-layer ceramics. On the KO, we've got these four SMD aluminum polymers from APAC, and that's APAC spelt like that. That's the actual brand of these capacitors. That's the same guys who are making the through-hole caps. Anyway, so we've got these, SMD aluminum polymers from APAC, and EVGA has just chopped off every multi-layer ceramic that isn't necessary. And I assume the reason why they went from, like, a lot of little multi-layer ceramics to just a couple SMD aluminum polymers, because this is worse from a ESL, ESR perspective. Like, lots of little capacitors in parallel is just better than a couple big capacitors in parallel. Okay, like, generally that's just how that works. And the thing is just like, I assume the reason why they went ahead and got rid of all the little multi-layer ceramics and just replaced them with these large SMD ones is it might actually be a matter of optimizing the time on the pick-and-place machine at that point. Like, it's not even about the cost of the parts themselves, though I do believe these are probably cheaper than all of the multi-layer ceramics combined. It's also like, well, now the pick-and-place machine has to place 4 components instead of... You know what? We'll just call that a lot of components, right? so that's kind of that. So basically, that also means that the card gets completed by the factory faster. If you just eliminate a bunch of components, the card gets to spend less time under the pick-and-place machines. And therefore, it can get through the production line quicker. And similarly, we have these 3, capacitor mounts right here. EVGA's only populated 1. If we look at EVGA's Nvidia's reference version of that, they've got the much more tedious version, with obviously better ESR, better ESL. They're going for their multi-layer ceramics, being very fancy with, like suppressing the transients from the core. And then EVGA is like, you know what, that just costs too much. Screw it. 330, aluminum polymer right there. Call it a day. Card runs at stock. Who cares about overclocking? And there is still overclocking headroom on, these cards. At the same time, I would assume there is just less overclocking headroom, not necessarily by a significant amount compared to, something like, say, the reference card or just other cards where it's just like, yeah, you like, because the thing is Turing doesn't scale that much with voltage, but at the same time, it's just like, this could easily be like 10, 20, maybe even like 50 megahertz of just like max overclock reduction here. Yeah, and it's just like, well, it doesn't matter because ultimately most people don't overclock anyway, and this card is obviously not meant for overclockers. This card is for people who want a cheap 2070 Super, and this is a cheap 2070 Super, and it runs. If you buy it, if you pull it out of the box, install it in your system, it'll run, it'll be stable, and it'll definitely outlast at least the warranty period, probably longer than that. Yeah, this card is just like, it's cost optimized, right? Like, that's the whole point of it. Yeah, anyway, where was I going with this? There was something I wanted to mention, and now I feel like I've forgotten it. Actually, I think that's it. That might be why I feel like I've forgotten something, because this video, I don't know, is 30 minutes, so it's not that short. What did I forget? Oh, okay, yeah, so I will mention that. So, from the Tech Power Up review, one thing I found interesting, because I did read through the well, I didn't read through the review, I skimmed through it. One thing I found really interesting is that Tech Power Up actually mentioned that this card runs at a relatively high fan speed. And actually, or not even a relatively high, like a rather high fan speed compared to other 2070 Supers. And apparently they reached out to EVGA about it, and EVGA was like, yeah, that's intentional. We intentionally run this card at a higher fan speed. And so I have a very interesting theory about this. My theory is because they've done all of these cost optimization things to the card, and I assume they probably didn't put too much effort in the cooling of various components, because obviously, like, thermal pads cost money, heat sinks cost money. So the thing is, if you're cooling anything with airflow, right, there's basically two factors that improve your cooling. One, the air being cooler. If you have cooler air, then whatever you're cooling is going to be cooler, right? If you're cooling something with 10-degree air, it's going to be cooler than if you're cooling it with 20-degree air. Simple physics. And secondly, how much air, right? If you just flow twice as much air over a certain surface, well, you'll be able to cool it more than if you flowed less air. So the high fan speed kind of achieves both of these effects because one, air going through because anything on the PCB is of course cooled by air that has passed through the fin stack of the heatsink for the GPU core. So that air you can basically consider it used air. And so the faster we can get the air through the fin stack, the less hot it is when it comes out of the fin stack, right? And we're also significantly increasing the amount of air that's running through the fin stack, so the amount of air hitting the PCB increases. So I honestly think that the relatively high fan speed of the card, because in the review you'll notice that the temperatures on this card are actually just fine, and I'm not going to give you specific numbers because you should go read the review if you want those. Like, the thing is just like, I don't think the fan speed is for the core. I think it's for the PCB, which really makes me wonder about, like, these power stages and those MOSFETs. Because the capacitors, those should be fine. If anything, these capacitors should have a better time dealing with high temperatures than the ones on the reference card. Because these are, SMD aluminum polymers. These are through-hole aluminum polymers. These are rated for 5,000 hours. These are probably rated for 2. So, yeah. you know, that's kind of that. So that's it for the video, basically. So EVGA's KO is basically less phases, cheaper capacitors, cheaper inductors, no less current balancing, added some fuses, which is neat, removed a lot of capacitors, right? And yeah, that's basically it. That's like how they you know, cost optimize the PCB for the price point they were aiming for. Though, admittedly, this is not the cheapest 2070 Super. At least at the time of making this video, I checked some prices. This is not, like, there are other cards that are basically similarly priced. Though I've not bothered to check the PCBs on those, because yeah, so I might be unfairly harsh here to EVGA. Like I should probably do like a comparison against the other cheap 2070 Supers. At the same time, do I actually care that much? Not really. Honestly, like I'm just doing this video out of like my random interest where it was like I saw the review, I was like, "Oh, neat. I wonder what EVGA did to lower the cost of this card." And then I saw the PCB and I was like, I want to compare this to a 2070 Super reference card. And so here we have a video. Because I did the comparison for myself, and then I was like, oh, this is actually kind of interesting. And then I was like, that might make a decent video, and here we are. And this is the end of the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, and, you know, the usual YouTuber merch stuff. And yeah, there's a link to that down in the description below as well. Both the Patreon and the Teespring help out immensely with running the channel, so if you'd check them out, that would be great. Thanks for watching, and goodbye.